So in this video we're going to be looking at energy, and then we're going to go and look at scalars and vectors. So we're asking the question, what makes a car go? The very simple answer to that question is energy. Energy makes a car go. But in this video we're going to be looking at it in a bit more detail to see exactly what energy transformations take place in a car to make it move. After that we're going to have a look at what a scalar and a vector is and the difference between the two. So we've previously met the law of conservation of energy. In an isolated system, energy is always conserved. If we want to change the energy of the system, then we need to do work on the system or transfer heat to the system, in which case it's no longer considered isolate. So let's now look at the energy transformations that take place in a car. A typical car has what's called a four-stroke engine. We're going to look at exactly how that engine works, and we're going to use this syringe as a model of that engine. So this syringe has a piston that will move up and down. So to start with, in the engine, the intake valve opens and the car does some work on the engine, so it pulls the piston down, and as it pulls the piston down, an air and fuel mixture goes in through this intake valve. So the cylinder in the car is now full of air with a mixture of the fuel in it as well. What happens then is that the intake valve is shut off and the engine does more work compressing this cylinder. So we've now got a mixture of fuel and air in there, which is all compressed. The car then ignites the spark plugs. So these cause a spark to take place in that mixture of fuel and air. And when that happens, the temperature increases very rapidly. And we've seen from the ideal gas law, PV is equal to nRT, that if the temperature goes up, then the volume goes up. So at that point, the gas here does work on the piston and the gas all expands and the piston moves downwards. This is the most important step in the process, as this is when the fuel is actually doing work on this piston, and so this is when the car actually gets the energy out of the fuel. So work is a way of transferring energy, and it is equal to the force times the distance. So the gas molecules in here apply a force on the syringe, and the syringe moves downwards. The force applied by the gas molecules is also downwards, and so we have positive work done. We are getting energy from the fuel. So the actual car itself is then gaining energy from that fuel. So now that this is expanded, this cylinder is full of spent fuel and air. So finally, to complete the cycle, the car does a bit more work on the engine. It compresses the cylinder, the piston, and that releases all the spent fuel and the air out of a release valve up the top. So we're now back to where we started. It can pull in another fuel-air mixture, compress the fuel-air mixture, there's a spark, it expands rapidly, releasing energy, and then finally it empties out again. So in a car, that chemical potential energy is released, and that does work on the piston. The piston's attached to a rotor, which goes round and round, which is eventually attached to the axle, which makes the wheels on the car turn. So we're converting the chemical potential energy into energy of movement.
So this clip shows a simulation of the Audi 1.8 litre petrol engine. So you can see that it's got 4 of these cylinders which all work simultaneously, so that 2 are moving down while the other 2 are moving up. This means that one of them is producing work, which drives the shaft to compress and expand the other 3 cylinders. Overall, you are gaining energy from this process from the conversion of the chemical potential energy.
Energy of movement has a special name. It's called kinetic energy. So the kinetic energy, the energy possessed by a moving object, can be calculated using the formula 1/2 times mv squared, where m is the mass of the object and v is the velocity of the object. So let's do an example now where we will calculate the amount of kinetic energy possessed by an object.
So the question is, our car has a mass of 1,400 kilograms. How much kinetic energy does it have if it's travelling at 60 kilometers per hour? So to answer this question, we're going to need to use the formula that the kinetic energy is equal to 1/2 mv squared. So m is the mass in kilograms and v is the velocity in meters per second. So the first thing we're going to need to do is convert this speed from 60 kilometers per hour into meters per second. So 60 kilometers per hour is equal to 60 times 1,000 meters per hour, and then to get it into seconds, in an hour there's 60 times 60 seconds. So these will cancel out and we end up with 16.67 meters per second. And so this tells us that the kinetic energy is equal to 1/2 times the mass, which is 1,400, times 16.67 squared. And so solving that on the calculator, we get 194,522. So we should only give this to 2 significant figures. So this is about 190,000, and the units are joules because it's an energy. The question goes on. If the car has a petrol engine with an efficiency of 25%, how much fuel does it require to reach 60 kilometers per hour, given that the energy density of petrol is 36 megajoules per litre? To answer this question, we're going to need to make use of conservation of energy. So conservation of energy tells us that the initial energy is equal to the final energy. Now, the final energy is in the form of kinetic energy, and we've just calculated how much kinetic energy it had. It had 194,522 joules. So we should keep all the significant figures while we're doing the working and then convert it back to the 2 significant figures at the end. Now, initially the energy is stored as the chemical potential energy. This is chemical potential energy. So the amount of fuel it needs to produce this much chemical potential energy, this one's the kinetic energy, is given by the efficiency times the energy density times the volume, and that is equal to 194,522. So the efficiency is 0.25 as it's 25%. So a quarter of the fuel is converted into energy, and then with the energy density is 36 times 10 to the 6 because it's 36 megajoules. So this is joules per litre times the volume, which is what we're trying to find. So now we can rearrange this. The volume is equal to 194,522 divided by 36 times 10 to the 6 times 0.25. So solving that on the calculator, we end up with 0.022 litres, which is equal to 22 millilitres.
So in this example, we did neglect friction. Friction actually turns out to be very important, and we will be looking at it in more detail in later videos. But basically, the frictional force is trying to slow the car down, and the car actually has to do extra work to overcome that frictional force. So if your engine stops working, the car would actually slow down as the car lost energy doing work on the friction force.